Very well. Hi, Fawaz. How are you doing?
Great, thank you. I think this is a great session to get this DevRel campaign started. So I'd like to welcome you to our community. Perhaps we can just do a little bit of introduction about you. Where are you based and what you do at Hazelcast?
Sure, sure. I am a principal architect at Hazelcast, and I work out of Atlanta. Although sometimes I move around, but but I'm most often in Atlanta. So, and my background is all basically either in professional services or in sales engineering type roles with in-memory data grid customers, either both Hazelcast and other in-memory data grid products as well. So I've been in that space for I think about 17 years or so. So this talk today is focused on architects and what we should be thinking about in terms of all this event-driven buzz.
Yeah, great. So 17 years is like long time. I'm pretty sure things have changed dramatically, especially last few years. So we had this discussion last week about event-driven architecture. So perhaps before we dive into this topic, can you tell us why this topic is important and what architects should look for event-driven architecture?
Well, I think that architects are probably, looking at tech talks and papers and things like that, and they're probably seeing a lot of event-driven things, a lot of buzz around event-driven, and we've all, if any architect that's been around for a while has been through a few buzz cycles. So trying to sort out the fad from the fat is something that we're all constantly trying to do. Is it just kind of the hot thing, or is there really some real meat here? So I'm gonna kind of share my view on event-driven architecture, and of course it's Hazelcast centric. I think Hazelcast has a unique role to play here. So that's what I'll be talking about. Yeah.
Yeah, it's a very excited topic. So I'm looking forward to it. So how about we start and get into it?
Sure. Awesome. I will share my screen. Okay, can you see my screen?
Yeah.
Okay, awesome. So as Fawaz and I were just saying, we're seeing a lot of event-driven buzz going on, and here's my thoughts on how we decipher this. So we know that that sort of some new tools. They're not that new, but some new tools have kind of burst onto the scene, and they're giving us new capabilities. And so part of what's going on is that architects are trying to figure out what new patterns and new usage patterns for those tools. So the big ones that I'm here to talk about today are basically your Kafka's, any kind of event log, basically durable event log, and then your stream processing engines. Those things work hand in glove, and there's a lot of patterns around them. Event sourcing, Saga, CQRS. These are all architectural patterns we've probably all at least heard of. So that's part of what's going on. And the other thing is the tools also influence. I mean, the architectures also influence the tools. And I think what's driving it all is businesses trying to basically move faster. So, kind of catch their customers at the most, in the middle of whatever they're doing, and make them an offer or give them information to help them make a decision. And that's all happening faster and faster. And so I think that's really driving this cycle of tools and architectures. Um, so I think we generally break down the world, architects will generally kind of break down the world into data at rest and data at motion. And, again, for the architects that have been around a while, I would say that, for the last really a couple of decades. Data, database, data warehouse, data lake, they're all data words. Data has been sort of the center. And now we've got this competing center with events. We've got event brokers, event sourcing, event-driven architecture, and so forth. And I also included here some. I also include here model training versus model scoring. So model training is just a very data intensive process where basically you feed a lot of data in, and what you get out is a very complicated function with a lot of parameters that's good at, for example, detecting fraud or making a recommendation. So it's very data centric. But then when you actually go to use the model, that's very event centric. So this data and event paradigm is also there in ML. But I'm really here today to talk about microservices. So where do microservices fit? So traditionally, they have been sort of in this data circle, but I say that they also fit in the event circle as well. So that's where we're going next. Let's update the concept of a microservice to encompass events. I think that's a lot of what's happening. So it's not just me. This is not the first time um, this has been attempted. I think this is just what architects are doing. Um, so what is it? Well, what is an event-driven microservice? It might sound pretty funny, but if you haven't already, if you just Google the term, you'll see talks going back to 2019 and before. You'll see material published by Confluent. It's definitely a term, and I'm here to kind of focus in on that. So let me just give a simple definition. An event-driven microservice is a microservice that follows the principles of event-driven architecture. Of course, that's a complete dodge. So now we have two more things to define. So that's what we'll do next. We'll talk about what is a microservice really, then what's the essence of it, and what is the essence of event-driven architecture. Okay, so this is just my definition, but hopefully some of these things will resonate. So it's really more than a thing. It's a methodology for decomposing the monolith into individual services, individual chunks of business logic. Um, and the real benefit is agility and time to market. So it allows businesses to innovate and kind of break away from the controls that go with a more monolithic architecture. When you have a lot of apps pointed at the same database, they can communicate very efficiently, but there's a very wide interface. There's huge, because it's just the whole schema, and there's huge potential for one changes to one app to impact another. So controls are usually implemented, and that slows things down. So microservices are, in this whole program of decomposing the monolith, are a way to get away from that. And so I would say anything that claims to be a microservice, if it doesn't deliver the benefit of agility, it's probably not really a microservice, because that's the reason that we do it in the first place. So traditional definition, they're small, independently deployable chunks of business logic. They're cohesive. They're usually focused on a certain business function, and they're composable. They can call each other, but only via an interface. So, usually the interfaces between microservices should be, very, very carefully defined. And this is probably the most important part. They're built by small autonomous teams. So, and the autonomy is the key. The teams need to be able to, in order to be fast and get to market quickly, they need to be able to be as self-sufficient as possible. And in doing that, they typically need their own data store. That's something
Can you
that's
comment on latency, Randy, here? Why microservices are important if the application requires have low latency?
Yeah, well, so I would say that, probably with at least a conventional microservice, you you probably end up with a more scalable architecture, but you may end up with an architecture, you may actually end up with higher latency. And you certainly end up with higher complexity. So it's all you accept those things because of the agility it gives you. But you know, I think we're going to show you a Hazelcast alternative, but just thinking about typical app server hosted web services, they add hops, and so it adds latency. Yeah,
Thank you.
thanks. All right, so what's not necessarily a microservice? Hopefully you agree with that definition. And so there is nothing in there about a request response interaction pattern, nothing in there about REST, nothing in there about application servers. So, they may be involved in a microservice pattern, but just because you've, say, used REST doesn't, make a thing a microservice. So here's the next question to think about. Does a microservice have to be request response? Now, I think it's pretty clear where I'm going with this here. My answer would be no, it could be, but some microservices react to events. Some microservices aren't necessarily request response. So example of that, any kind of status update. So let's notify the customer when the pizza is out of the oven and out for delivery. You certainly could write a REST service for the cell phone to check constantly, right? You could have your cell phone constantly polling to see the status of the pizza, but it's not the most natural way to model it. It's not going to be great for your cell phone battery either. The most natural way to model it is as an event, right? And yet it's still a cohesive unit of business logic that you want to be able to evolve independently. So I say that is a microservice. Tell the customer when their parking is about to expire. Similar idea. It's also business process orchestration category that will commonly have event-based microservices. So, for example, in logistics or in basically order fulfillment, after a customer has placed an order, we have to see where is the customer, where is the stock, and then we have to issue pick orders to each warehouse, maybe multiple warehouses, and essentially make a plan and orchestrate a plan for getting that order fulfilled. So that's definitely a kind of a independent business function, but it consumes and emits events. It's not necessarily just a request response. Another example would be in retail. Maybe we have a policy that after a cart has been abandoned, this is online retail, after a shopping cart has been abandoned, we should put anything that was held in the cart back in inventory, and we should add those things to the customer's suggested purchase list so they can find them again later, maybe buy them again later. So again, I think these are all, units of business logic that you want to be able to evolve and deploy and evolve independently. And so I think these are all microservices, but they're event driven. So there's my high level answer to what is an event driven microservice. Now let's talk about what are the principles of event driven architecture. And again, this is just my take on it, but I have looked at a lot of literature and papers and just thought about it, and I think these 5 things are the top things that distinguish an event-driven architecture from a more traditional microservice architecture that we're all familiar with. So, I'm starting at the bottom. So event-driven architectures are just inherently asynchronous. Traditional microservice architectures might or might not be asynchronous. So I have an example here for this. So I've done a lot of consulting and a lot of performance tuning as a consultant. And so I had a friend that I was just meeting at the bar, and he asked me what I was up to, and I told him about this customer I was trying to help with their performance. And I just said, I don't understand why it doesn't use more CPU. And he thought that was a very strange way to look at it, but actually it's not. What I found is if you have an application that uses a lot of CPU, yes, you may be able to do profiling, and if there's unnecessary code in there, you may be able to make it more efficient. But ideally, a lot of times that's a good thing because it means you can just add hardware and get more throughput. So the trickier situations to deal with are situations where, as you add load, suddenly the throughput starts to level off, but the CPU doesn't go up. That's that's a harder problem, and it ties in with sync versus async, or blocking versus non-blocking. So any kind of synchronization or waiting can cause basically make it difficult to scale. This is something that you can get when microservices call microservices. So I have an analogy that I hope will kind of drive it home. So it's called the sneaky food truck. So here's the sneaky food truck business model works like this. So you walk up to the counter and you place your order, and unbeknownst to you, out the back door, they dispatch a scooter to an actual real restaurant with a real kitchen and two cooks. They prepare that meal and then they send it back. And this is, if the analogy is not clear, this is like a microservice calling a microservice. So the scooter is is slow, and that represents the network. Okay, so the first service is taking the order, and the second service is um, cooking the order. So, all right, here is the sneaky food truck runbook version 1, which is completely synchronous. Okay, and we don't have to understand this in complete detail. I'll just kind of quickly narrate it. Here's how it works. Customer 1 walks up to the window. Order taker takes an order. Order taker, it takes about a minute. Order taker dispatches it, and by minute 2, a cook is working on that order, and the order taker is just waiting for that to come back. And by minute 13, the meal is back, and by minute 14, the order taker has put it in a bag and given it to customer 1. And then the order taker just repeats it. It goes, and the order taker goes and asks customer 2 what customer 2 would like. The whole process starts over again. Well, this is not very efficient. For one thing, we're not ever using both cooks at the same time. So it's like, why doesn't it use more CPU? And the answer, hopefully the answer in this case is obvious. The order taker should probably not wait for that to come back. The order taker should just go on. So in this synchronous methodology, we're basically getting a meal out every 14 minutes. Okay. In this async methodology, what happens is the order taker, after taking the first order and dispatching it, the order taker immediately takes the second order. And the consequence of being async is that we're actually the second meal, and rather than arriving at 28 minutes, arrives at 16 minutes. So we're getting a meal every 8 minutes versus every 14 minutes. So so much faster, and we're utilizing both cooks. We're utilizing more CPU. So and this is a completely obvious thing, but a lot of times we build systems this way, and hopefully using this example kind of unpacks it. So it's very important. It's very important to in a scalable distributed system to use async interactions wherever you can. And this is one place where Hazelcast really shines. So hopefully that's hopefully that makes sense about synchronous and asynchronous. All right, so I'm hopping back up to the top now. Okay, APIs define communication versus events define communication. So we all know what an API is. So the event-driven world's a little different. And by the way, something I wanted to say here is that I regard this as just another lens to look at the world through. I'm definitely not saying that you should all forget everything you know and start doing, only pure event-driven design. I'm trying to look at it in its pure form so that we can talk about it, but it's another lens to look at the world through. You still, I don't think it's possible to really replace an architect's judgment. So, but it's an interesting lens. So let's talk about it a little bit more. So, in the event-driven world, an event, a service emits events, and it basically is just a complete recording of what happened. And the service that emits the event isn't really overly concerned with, how do people want to use this event? Not at all. In fact, the job of that service is just to publish the event, and then over time, multiple consumers will be written that will consume that event. So the interface between systems now becomes the event definition, which obviously that makes schema very important. Okay, this is one of the hardest things for me personally, as someone who's learned about object-oriented programming in probably the early 90s. This is a huge shift, but event-driven architecture and design is more verb-centric, and we've all been taught traditionally to look at the nouns, and that'll help us understand the system that we're trying to build. Now, I will say that there's some things that may sound like nouns that are really actually kind of verbs, like orders. So orders are, the noun is just, hey, it's just a recording of something that happened. So orders are a great example of, orders are really, I would say, an event. So maybe it's not as alien as it first sounds. Okay, services consume and send events on the one case versus respond to requests in the other case. Okay, and then this to me is probably the hardest thing, and I actually don't know of anyone that actually takes this completely literally. At least I haven't seen it. But databases are the source of truth versus event streams are the source of truth. So in an event-driven architecture, in theory, you would be able to throw away all the databases and then reconstitute them from the event stream. So the event stream that's what it means by the event stream, is the source of truth. And it goes along with the idea that every service gets its own database. Hey, that one got Fawaz back on. What's up?
No, it's just I think this is an interesting topic. Just to clarify, are you saying it's gonna be only event streams for the event-driven architecture, or is it event streams as well as databases?
Yeah, so we'll definitely not only event streams. It's just that event-driven architecture, again, only in the pure form, which I don't think anyone 100% subscribes to, kind of looks at databases as disposable, and you can always reconstruct them from the event stream, and the event stream is the source of truth, but you still need the databases. So hopefully this example is going to make it a little bit clearer. All right, so let's go with the traditional order process, or just online retail system, because everybody understands the entities. So we've got a legacy system. It's got everything in it. It's got orders, it's got shopping, it's got fulfillment. Everything is in this system in a single database. And the owner of the system wants to be more agile. They want to start carving out microservices. And what is the event-driven approach to this? So I think it's a good thought experiment. So let's start with orders, and let's say, oh, well, we'd like to pull out an order service, and because we're not looking at this 100% pure, we're still gonna have like a REST interface that the shopping UI can call. So we're gonna write a new shopping experience, and we're gonna put it on top of this order service, and it'll interact via REST. But this order service is going to publish the orders, and then we're going to eventually write other systems that that consume those orders, fulfill them, and whatnot. All right, and notice I have a customer story here, even though customers are also in the legacy system. So that's the first thing we have to deal with. So in the event-driven way of dealing with that is to basically liberate the customer data by changing it into events, publishing it to a topic, and letting the order service consume that and create its own store. So this, this might be an in-memory store. It might be Hazelcast, in-memory data grid, which would make your order service very fast, right? So it's, you know, we're we're starting to now diverge from the purely classical microservices where everything has to be a hop. So so order service gets its own customer store. We do some sort of customer CDC in order to change the customer data into events. And one of the things that you'll see, the kind of buzzwords you'll see, is liberating the data. So now this data is liberated and other systems can now start to consume it. Okay, so there's one thing that's missing from this picture, even for orders, is so I'm sure that in this legacy system here, there are still things that we didn't carve out that need to see orders. Maybe it's some business intelligence reports, or could be any number of things. So to complete the picture for the order service, we have to actually, we actually have to send, basically have the legacy system consume those events some way and put them in the database for those other apps that haven't been migrated yet. So at this point, we've successfully carved out one service, and now the order service can be, independently evolved. All right, so what's next? Maybe, and by the way, in case it's not clear, so now the order service becomes the master for this order data, and the legacy systems are just reading it. And obviously, you have to be making decisions. Typically, you're only going to have one service be the master of a given data type. Okay, so let's add a shipping service. So now the shipping service is going to subscribe to that order topic. It's going to, by the way, it's going to have its own, I didn't draw it here, but it's going to have its own customer store. So it's also subscribing to customers because it has to know where to send the items that are being shipped. Got to get that address. So it's got to subscribe to the customer. But it might be a different data store. It might only have the minimal picture of the customer that's needed in order to do shipping. But anyway, the shipping service is going to have side effects and eventually is going to emit, side effects that cause the shipment to actually happen. And it eventually is going to emit events letting other parts of the system know that, hey, shipments have occurred. And then I think you get the idea. We're going to maybe add one more, notification service. So whenever an event is sent, we want to tell the customer, but the shipping service doesn't have to worry about that. It's all about shipping. But the notification service needs the customer's phone number, or the way to contact the customer. So it also needs to subscribe to customer data. So that's kind of an example of using those principles to design an event-driven system. Hey, Fawaz.
Yeah, so I think this is great. So can you just clarify what orders and shipments are? Are these queues or are these like topics in Kafka?
They're topics in Kafka is what they
Okay.
really are. Yep.
Mhm.
Anyone, so in that way we can have multiple consumers. We have multiple consumers of customer data, for example.
Thank you.
Awesome. All right, so now, okay, that's just kind of the whiteboard diagram, but now let's look at the tech stacks that are involved in this. And obviously, this is where we're going to bring in Hazelcast. Okay, so you got a few options for doing this. One thing I think that I think is probably true is that everybody has to deal with request response type, services and event-driven services. That's I assume that's going to be the case for any big business. So how do we, what's the architecture for handling both those things? Okay, so this is option one. If I was going to guess, it's just a guess, but I would guess this might be kind of the most common where industry is at right now. So all business logic is still in the app server tier. It's still independently deployable chunks of business logic, but some app servers, some microservices may subscribe to topics and publish to topics instead of taking HTTP requests. And then you're always, just constantly, if you imagine constantly hitting like maybe a customer database to do constant customer lookups every time something related to that customer happens, that's just not really the way databases like to be used. And it's not going to be fast enough. So almost always in these architectures, you're going to have, by the way, the other thing is you may need a read-only copy of the data. The master may be, the actual master may be owned by someone else, some other system. So for those reasons, you almost always will end up with this fast data layer that that basically makes it quicker and more efficient to access the data that you need in the microservices. And this is one of the ways that, by the way, that Hazelcast is used quite often. All right, option 2, I just changed options. Here, the app server moved over here. The app server is only dealing with request responses, and stream processor, which is a product category. If you're not familiar with it, the stream processor is handling the events. And you still have a fast data layer. They both still need to be able to, all the data is not going to be on the event. They need to go and, potentially look something up. All the data is not going to be on the request. The app server needs to go and look something up. So, you have this fast data store. And then stream processors are built just from the ground up to process events. So they're in a lot of ways, they are the ideal host for event-driven services. And maybe that could be a topic for another talk. But Hazelcast has a stream processing engine. And so we're going to talk about that just a little bit. Okay, third option. Here's an interesting thought. Since stream processors have all these good qualities and they're async from top to bottom, we could just decide that a request was just an event. Hey,
apologies, we can't see the option 3 now, so it's just on option 2. Yeah, thank you.
There we go. Option three. Thank you. Okay, so we could just, if we just consider a request to be just another event, then we can actually serve both request response type services and event-driven services out of the same infrastructure stack. Okay, so keep that in mind. And then let's now put specific technologies on here. And of course, this is always changing. My list is sure to omit some important ones, but let's just look over some of the most popular ones in each category. So message broker, we've got Kafka, Red Panda, Pulsar, probably others. In the stream processing world, we have Kafka Streams, and we have Flink, we have Hazelcast. The cloud providers have their own offerings for this stream processor category or event processor category, whatever you want to call it. And then there are also a lot of fast data stores, including Redis, which is popular, and Hazelcast, which is popular. Well, I want to call out something here. Look, Hazelcast actually has a role to play in both the stream processor world and the fast data world. So with Hazelcast specifically, we can have an architecture that looks like this, which is much simpler, right? So the stream, so basically a microservice becomes what we call a pipeline. A pipeline is just something that consumes events and publishes events. You write it, and Hazelcast deploys it. That's the essence of it. But the cool thing about this is that we've taken out another hop. So whenever I'm processing an event and I need some data, I can look it up, and it may very well be actually in the same process. So that's microseconds versus milliseconds. So the implications to throughput are huge. Not because anyone cares about a single millisecond. It's that it adds up. So okay, so I want to kind of take this idea and flesh it out in a real world example, and that's kind of where we'll leave this. Okay, so the example is machine monitoring. Jump the gun there a little bit. So imagine you've got a factory that every machine is instrumented, and it emits data, and we need to monitor that data. And we've got, I'm going to simplify the business, and we say we only have two services. Um, one's to basically digest that event data and summarize it, compute summaries. I would like, a 10-second window, 10-second rolling average of the bit temperature on every single machine. That's an example. So that's one service. Then another service is a more conventional request response. Hey, for a particular machine, I want to get that average bit temperature as of when I ask for it. But I also want to, for a specific machine and a specific configuration, the acceptable range of temperatures might be different. So I need to combine the information about the bit temperature of that machine with information about the parameters of that machine, and basically categorize it. It's 250 degrees and that's green, or it's 260 degrees and that's red, that kind of thing. So how would we implement this service in Hazelcast? So here's a picture. This whole box is a Hazelcast cluster. Let's just kind of look at the outside. Whole box is a Hazelcast cluster. The events coming from the shop floor are being published to, let's just say, a Red Panda topic, or it could be an MQTT topic. If this is IoT, it's probably more likely an MQTT topic, but they're being published. And so the system, and the Hazelcast system as a whole is consuming them. And then we still need to be able to make that request for the current status of each machine over just plain old REST, and we still want a REST service. So we have like a web service proxy that just simply takes the REST request and turns it into an event that can be processed. So the two gray boxes are two services. This service is the machine status service. This service, and it doesn't really matter really what's in it. Let's focus more on just the fact that it's a deployable piece of business logic that you can evolve separately, whose job is to basically report on the machine status. So and it's in Hazelcast parlance, that's a pipeline. So but you could think of it as a service to process events. Okay, so we've got one whose job is to do that, and we've got another pipeline whose job is to compute those aggregates. And again, Hazelcast platform lets you deploy these things and evolve these things independently. And then we use maps, the in-memory data store, to mediate. So the Hazelcast, the event summarizer average bit temperature over the last 10 seconds writes to a in-memory machine aggregates map that just reflects the current. It's almost like a digital twin, right? It's just the current state of the machine reflected in memory, kept up to date, to the second or even sub-second. Okay, and then this other response is this other service is then taking that data and also data about the machine profile and producing a response, kind of categorizing it red, green, orange, whatever. And the cool thing about Hazelcast is that, so in this particular case, we would partition this problem by machine. And what that means is that we can have all the profile data for, let's say we have a cluster of 5 machines. We can have all the profile data for a fifth of the machine, for a fifth of the machines in, in one node, in one Hazelcast node, and process the events that are relevant to those machines in that same Hazelcast node. So this is very fast and very scalable. And because it leverages Hazelcast event processor, it's async from top to bottom. So that's basically what I have for you today. I wanted to I'll just do a little wrap up. Hey, Fawaz.
Yeah, that's great to hear. Actually, very interesting topic. So I've got a couple of questions here, if you don't mind. So is
Fire
it
away.
basically or between traditional microservices and event-driven, or is it an and? So is it possible to have both cases, both types of microservices in the same application?
I think every business actually does have both, and one of the cool things about Hazelcast is it actually has, as a platform, can easily handle both. So yeah, I think just as a practical matter, everybody, any business of any size probably has both.
So one interesting thing about option number three actually is the combination between the stream processing and the fast data store. So um,
Exactly.
is there a way to basically say by using one platform, which is in this case Hazelcast, you're trying to minimize latency because as you add more tools or more frameworks, you actually increase latency when these two tools communicate. Is that true?
Yeah. Yes, totally true. That is why the Hazelcast platform is built this way. It's very, in my opinion, very thoughtfully built, um, to minimize latency. And so, yeah, and what's great about it is it's because of the way partitioning, or if you're not familiar with that term, like sharding, works with Hazelcast. Um, it can be kind of application domain aware. So in my example with pipelines, I'm sorry, with machine monitoring, it, it can be, you can kind of partition the whole problem by machine. And you basically, most business operations only pertain to one particular machine. And while you're doing those operations, you don't have to have data from any other machine. So you get this shared nothing architecture where all the data you need to process the event is right there in memory. Not every problem breaks down so neatly, but if you do have those kinds of seams in your application, then you can exploit them. You can use Hazelcast to co-locate by whatever makes sense.
Yeah, that's great to hear. Thanks so much for your time. I realize this is very important topic and many will look forward for a follow-up to see the actual implementation. So for anyone watching us live or recording, feel free to leave your questions on our community Slack or follow us on Twitch. Any final thoughts, Randy, you want to share, or what we plan for a follow-up for implementation or GitHub or anything like that?
Yeah, so I this is all not vaporware. It all is working, and you can I'd love to come back and show people that example. It's it's probably not all public on GitHub right now, but I need to do a little cleanup, and by the time I come back, we can have it all public.
Yeah, that's great. Thanks so much, Randy, for your time today. Yeah.
Thanks
Forward
very
for next
much.
one. Thank you. Bye now.
Take care. Bye
Bye.
bye.